Hi there. For this video, we'll be having an introduction on what inequalities are, specifically on the algebraic sense. So first, a good question to ask is, what are inequalities? Well, we know that in real numbers, we know that 6, if we compare it to 5, comparing the value, not the size out here, since clearly 5 is bigger. By comparing its value, we know that 6 is greater than 5. For -1, we know that -1 is less than 5. For 0, clearly 0 is also less than 5. For 3.1, this is a decimal, we know that this is less than 5 as well. And lastly, if we have 100, we know that this is greater than 5. Now, what if we have, say, a variable x? There, x, and we compare it to 5. Now, we know that in equations, we simply have x equals 5. But for this case, what if we want to know all the values of x that would make this inequality hold? So this is where the concept of inequality comes in. Since x is just a variable, so it can take any values, if you want to restrict its values to only values that are greater than 5, such as 5.1, 6, 7, 9, so on, we'll be needing to use the inequality sign. And the same goes if it is less than 5. Again, since x is a variable, it can take on any values, such as, in this case, it can be 4, 3, 4.999, and so on. So that is why inequalities are important, so that we'll be able to restrict the value of a certain variable in algebra. So that is the first thing that we need to remember in the study of inequalities. It's like restricting the value to a certain solution set or certain set. Now, with that out of the way, an important concept in inequalities is the idea of strict and non-strict inequalities. So when we say an inequality is strict, then we have either this greater than, or we can also have less than. So why is it strict? It is strict because this algebraic expression out here can never be 3. So it will always be not 3. So this can take on values such as 3.000001, but it can never take on 3. Now, when we say an inequality is non-strict, then we can either have greater than or equal to, or less than or equal to. So the presence of equal to or equal to out here is the reason that this inequality becomes non-strict, since 2x plus y out here can now be equal to 3. So that's just an important thing to take note, since oftentimes in solving inequalities, you'll see this symbol out here with an equal to sign, as in some cases, it's nice to solve non-strict inequalities. Another good thing to think about is how can we represent inequalities. Let's have, this is an example. Let's have, see, this one is A, and I know that the line is not perfect, but just bear with me. So there. So how do we represent this inequality? We know that if a value, say x represents these values out here, then we say that x is greater than a. And this is like the informal way to represent it, but formally we can represent inequalities in two ways. We have the set notation and the interval notation. So in terms of set notation, we represent this inequality out here as the set of x that is a real number such that x is greater than a. So it's just like a formalized version of this one. For the interval notation, we represent this one as a to positive infinity. So note that we use a parenthesis out here because a out here is not included. As you can see, it is hollow. So there's a hole. And we use the idea of infinities out here since, as we can see, the number line out here extend till infinity. So these are the two ways to represent inequalities, but it might be hard to grasp at first, especially if you don't have a background on inequality. So we'll dive into more examples and more cases in how to represent inequalities. Now, connected to this one, what if, say, a is included? Then we know that informally this is x is greater than or equal to a. So to adjust the set notation, we simply add an equal to here. How about for interval notation? Well, what we can do is we can replace this parenthesis out here with a bracket. And now these are the representations of this inequality. Let's have a different example. There. What if we have, there. What if we have, say, this one out here This one is C. And this one extends there to the left. Let's make it hollow first. So we know that formally we can represent this as x is less than C, since all of these values out here are less than C in our number line. So in set notation, we simply again copy this one. So we've got here x less than C, and for interval notation, we represent this one as, sorry for that one, right here. In interval notation, we represent this as -infinity to C, since the values are from here, the -infinity side going to C. If we want to include C, simply add an equal to out here, an equal to out here, and replace this one out here with a bracket. And these are the representation for this inequality. Now, what if we have this one, and this one is A, and this one is B? What if we have this case? We know that if x is a value, this one, we can represent it as x is between A and B. This one out here is actually called a chained inequality. So, chained inequality. Or chained notation, if in terms of notation, since x is like bounded from left to right, so it's like chained. So to represent it in set notation, we'll simply again copy it. So we'll have here x is between A and B, and for interval notation, again, since these two are hollow, or there are holes, we represent it as A to B, like that. If this one is shaded, then we simply change this to equal to, and then equal to out here, and we change A out here as bounded, or a square bracket. If B is included as well, then we simply add an equal to out here, add an equal to out here, and replace the B out here, or the parenthesis on B out here, with a square bracket. That is how it works. So just a last example, or last set of examples for this representation of inequalities. Let's have this case wherein we have here A and we have here B. So how do we represent this? We know that we have here x is less than A, since these are values that, if these are the values of x, then x can be any value that is less than a, since it extends on the left side. For the one on the right, we have x is greater than b, since all of these are values that are greater than b. So with this in mind, we have x is less than a. Then we also have x is greater than b. So we represent this with or. So we say that we have x is less than a, or x is greater than b. Note that we use or in this case because in sets we use the word or for denoting that x is a union of these two. If we use and out here, that means we're getting the intersection, which in this case, there are no intersections for this interval on the left and interval on the right. So using the and word is wrong for this one, and we use or instead. So to set it up on our set notation, we simply copy and write x is less than a or x is greater than b. For interval notation, similar to sets, or out here represents union. So we'll have here, first the interval on the left is from negative infinity to a, union from b to positive infinity. So negative infinity out here to a, then b out here to positive infinity. So like that. And similar to our previous examples, if we simply include this one, then this becomes an equal to. We add an equal to out here, and we change this one to a square bracket. And so those are our examples for representing inequalities. I hope that by this time you have a good grasp on how it works. Now, just some final thoughts. We have what we call the open and closed intervals. So in this case, if we represent this one out here in a number line, then we'll have here a and we'll have here b. For this one number line, we'll have here a and we'll have b out here, but it is included. For the last one, we have a and b out here, both included and connected. So for open intervals, we say that an interval is open if either both of these are parentheses or at least one is a parenthesis. So basically, this means that an interval is open if one or both of its endpoints are not included in the solution. So for this case, there are hollows out here. So we say that the first two are open intervals. For the last one, we say that an interval is closed if it has two square brackets, or the endpoints are both included in the solution. So we say that for this last one, this one is closed. So just important things to keep in mind in dealing with intervals. And the last concept is bounded versus unbounded intervals. So if we represent these, for the first we'll have a out here and b out here. Then for the next one, see if this one is c, then this one is from negative infinity to c out here. Then for D, this one is from D, oops, C must be included out here, D to positive infinity. So we see that an interval is bounded if the endpoints are both real numbers. So in this case, A and B are both real numbers. So we say that the first one is bounded. Or basically, the endpoints in the first example are concrete, and I guess you can visualize it in a sense. But for the two examples, the two last examples, observe that we have negative infinity and positive infinity. When negative infinity and positive infinity are present, we say that that interval is unbounded. So intuitively, it is indeed unbounded since it just extends out here and it never ends, so it is unbounded. This one also extends just on the right, so it never ends as well. But for this one, we know that there is a certain end out here and end out here, so that's why it is bounded. So take note of this concept as well, as it is important and kind of valuable to keep in mind in dealing with inequalities. Now, to formally end this, here are two exercises that you may want to work on. So for this one, we have this interval out here. Oops. I forgot to write the numbers. So this one is 0, this one is 1, and this one is -2. Now your goal for this first case is to represent this one in terms of interval notation. And for the second case, your goal is to represent this one in set notation. So that's it. I hope you enjoyed this one. It's kind of long video, but for the next videos, we'll now be dealing with how to solve inequalities like linear inequalities or some polynomial inequalities like quadratic and so on. So this video is just like an introduction, so there aren't really any examples to really challenge us in this video. So that's it. I hope you enjoyed this one, and feel free to comment down below your answers to these exercises, as well as if you want some clarification on the examples we had above or previously in this video. So that's it, and that's all for this video.